Welcome back to the deep dive. Today we're tackling a topic that is, I think it's fair to say, famously intimidating. We're talking about Hamiltonian mechanics.
It definitely has that reputation. You see the equations, all the partial derivatives, and it feels like a barrier.
But the core ideas behind it are so incredibly powerful. And that's what we want to get at today.
Exactly. This is maybe the most elegant reformulation of classical mechanics ever. And it all started with this ancient, really fierce debate about what force even is.
Our sources for this deep dive are perfect for that. We've got the history, tracing what's called the Vis Viva dispute. We have the core concepts, kinetic and potential energy.
And then we get into the Hamiltonian structure itself and follow it all the way to its relativistic consequences.
So our mission today is really to unpack these key pieces, kinetic energy, which we call T, potential energy V, and the Hamiltonian H.
And we want to show you how understanding this framework is, well, it's kind of a shortcut to becoming really well-informed about fundamental physics.
All right, let's start at the beginning. We have to go back to the 17th and 18th centuries. Newtonian mechanics was king, but it had its limits.
It did. For complex systems like, say, fluids or rigid bodies skidding through space, it just wasn't enough. And this led to this long, long war over conservation principles.
The Vis Viva dispute.
That's the one. It was basically a philosophical and mathematical fight over what gets conserved when things move.
So on one side of this fight, you have Descartes. He's arguing for something he called the conservation of motion.
Right, and for him, that was the product of a bulk and speed. So m times v, but importantly, not as a vector.
Just a number, a quantity.
Just a quantity, no direction. It was rooted in his belief that all space was, filled with matter and motion was this intrinsic thing.
And on the other side,
you have Leibniz, and he was fiercely opposed to Descartes. He put something called Vis Viva, or living force.
And his formula was different.
Completely. It was bulk times speed squared. So m times v squared. His argument was that you have to estimate a force by the effect it can produce.
Which connects back to Galileo, right?
Exactly. It traces right back to Galileo's finding that the height an object falls is proportional to the square of the velocity it picks up. So for Leibniz, mv squared had to be the real conserved quantity.
So we've got this intellectual brawl between mv and mv squared. It sounds like a simple math error, but it's much deeper.
Oh, it was a profound philosophical split. It was about work versus inertia. Is motion a state, or is the ability to do something?
So who broke the stalemate?
Well, the key insight actually came a bit earlier, in the 1660s, from Christian Huygens. He was studying elastic collisions.
Like billiard balls hitting each other.
The classic example. And he found that, both sides were kind of right, but also wrong. He showed that in these perfect collisions, two quantities were conserved.
Okay, what were they?
First, he found there was a conservation of what he called directional motion. That's what we now call linear momentum. M times v is a vector.
So Descartes' idea, but with direction tacked on.
Exactly. But second, he also showed that the sum of the magnitudes times the velocity squared, the mv squared, was also conserved.
So if Huygens figured this out in the 1660s, why did the argument keep going for another century?
Because it only worked perfectly for perfectly elastic collisions. When people looked at soft collisions, where things get deformed or stick together.
The mv squared seemed to disappear.
It looked like it was lost. But Leibniz had this incredible foresight. He argued it wasn't lost at all. He said it was just transformed.
Transformed into what?
Into the undetected motion of the tiny parts of the objects, into heat, into vibration. He was basically arguing for the general conservation of energy long before the term existed.
And that entire war, that whole debate, that's what gives us the two concepts that are just foundational to all of mechanics today.
That's it. This is a transition from force to energy. And it starts with kinetic energy, usually written as T, or E sub k.
This is Leibniz's idea, really. The energy something has, just because it's moving.
It is. The modern formula is 1/2 mv squared. That 1/2 factor is really just a convention to make it line up neatly with the definition of work.
But that v squared term is the crucial part, and it has really immediate, real-world consequences for all of us.
It really does. I mean, think about driving a car.
The stopping distance example.
The perfect example. If you double your speed, say from 30 to 60, you haven't changed your mass. But the kinetic energy goes up by 2 squared.
So 4 times the energy.
4 times. Which means if your brakes apply the same force, you need 4 times the distance to stop. That energy scales non-linearly, and it catches people out.
And this idea of energy of motion isn't just for, cars moving in a straight line.
Not at all. It scales everywhere. Rotational kinetic energy is 1/2 I omega squared. It's the same quadratic form. In fluid dynamics, the kinetic energy per unit volume is called dynamic pressure, 1/2 rho v squared. It's the same idea over and over.
Okay, so that's the energy of motion. Now let's talk about its opposite,
Yep.
potential energy, usually V or U.
Right. And this is the energy of position or configuration. It's stored energy, the capacity for motion.
And it's only associated with certain kinds of forces, right?
Only with what we call conservative forces, things like gravity or a spring. Forces where the work you do to move something doesn't depend on the path you take, just the start and end points.
And that's what gives us the mathematical link between the force and the potential.
Precisely. The force is the negative gradient of the potential field, which, in simple terms, just means the force always points in the direction that the potential energy decreases the fastest.
Like a ball rolling downhill.
A ball rolling downhill. Gravity's pulling it from a place of high potential energy, RH, to a place of lower potential energy.
So in a perfect system with no friction, you get this constant trade-off.
A perfect trade-off. Think of a mass on a spring, oscillating back and forth. The energy is constantly swapping from kinetic when it's moving fastest.
To potential when the spring is most stretched or compressed.
And the sum of those two, the total energy, remains absolutely constant. And that sum, that total energy, is what leads us straight to the Hamiltonian.
Now, you often hear that the Hamiltonian H is just the total energy, T plus V, but our sources are really clear that this isn't always true. It's more of a special case.
It is a special case, an excellent point to bring up. For H to equal T plus V, 3 conditions have to be met.
Okay, let's break them down.
First, the potential energy, V, can't depend on velocity, so, no forces that get weaker just because you're moving fast. Second, the kinetic energy, T, can't explicitly depend on time.
Meaning the rules of the game can't be changing as you go, like a spring whose stiffness isn't constant.
Exactly.
Yeah.
And third, T has to be what's called a homogeneous quadratic function of the velocity, which is a fancy way of saying that kinetic energy has to scale exactly with V squared.
Which it does in normal non-relativistic mechanics.
It does. So for most classical problems, you're safe to assume H equals T plus V. But the real genius here isn't the sum itself. It's the whole analytical structure that Hamilton built around it in 1833.
This is where we get the big shift in perspective. Before Hamilton, you had Lagrangian mechanics, which uses position and velocity.
Right. Q and Q dot.
Yeah.
Hamilton realized that to get simpler equations, he needed to change the variables. He switched the focus from velocity to momentum.
From Q dot to P, this is a big deal.
A huge deal. He uses a mathematical tool called a Legendre transformation to swap them. You get this new function h, which depends on position and momentum instead of position and velocity.
And why go to all that trouble? What do you gain?
You gain a new way of looking at the problem, a new space. You move from our normal 3D coordinate space into something called phase space.
And phase space is this higher dimensional space where position and momentum are treated as equally fundamental coordinates.
Exactly,
Yeah.
symmetrically. And the payoff for working in this new space is incredible. Instead of one complicated second-order differential equation, you get 2 beautifully simple first-order equations.
These are Hamilton's equations.
These are Hamilton's equations. The rate of change of position is the partial derivative of h with respect to momentum. And the rate of change of momentum is the negative partial derivative of h with respect to position.
That symmetry is just stunning when you see it written down. And it unlocks these amazing shortcuts.
The most powerful one being the idea of a cyclic coordinate.
Okay, so what is a cyclic coordinate and how does it help?
Well, look at that second equation. The change in momentum depends on how the Hamiltonian changes with position.
Right.
So what if the Hamiltonian doesn't change with a certain position? What if a coordinate, let's call it q, just doesn't appear anywhere in the formula for h?
Then the partial derivative with respect to that coordinate would be 0.
It would be 0, which means the rate of change of its corresponding momentum, p, is also 0.
That momentum is conserved. It's a constant.
It's a constant. You found a law of conservation just by looking at the geometry of the problem without solving anything complex. You've simplified the entire system.
The example from the source material was the spherical pendulum.
A perfect one. A pendulum swinging in 3D. Its energy doesn't depend on its horizontal angle, its azimuth, which we call phi. It only depends on how high it is.
So the phi coordinate doesn't show up in the Hamiltonian. It's cyclic.
It's cyclic, and therefore its corresponding momentum, which in this case is the angular momentum around the vertical axis, has to be conserved. It must be constant. And knowing that makes solving the rest of the motion so much easier.
So this whole structure, this focus on momentum and these symmetries, this is why Hamiltonian mechanics becomes the bridge to modern physics.
It is the bridge. Absolutely. When physicists were developing quantum mechanics, they didn't go back to Newton. They started here. The algebraic structure of Hamilton's equations, especially something called the Poisson bracket.
We don't have to go there.
We don't. But that structure is the direct precursor to the Schrödinger equation and the entire quantum framework. It's the language that connects the two worlds.
So let's cross that bridge. Let's make the final leap into the 20th century and connect this total energy concept, H, to perhaps the most famous equation of all.
E equals mc squared.
How does this classical framework lead us there?
The link emerges when you look at the full relativistic formula for energy. At low speeds, it simplifies down into two parts. You get the classical kinetic energy, 1/2 mv squared.
And you're left with this other term.
You're left with a constant term,
Yeah.
mc squared. The rest energy, the total energy of any object, even when it's perfectly still, includes the energy locked up in its mass.
Okay, so if the Hamiltonian is the total energy, T plus V, this must mean that potential energy, V, also contributes to mass.
It has to. And the thought experiment in our sources shows this beautifully. Imagine a system at rest. A big mass, m, and two smaller masses, m, held apart by powerful compressed springs.
So there's a lot of potential energy, E sub P, stored in those springs.
A ton of it.
A
Now,
ton.
you release them, and that potential energy converts entirely into the kinetic energy of the two small masses flying apart. Simple enough.
Okay.
But now, view that exact same event from a reference frame that's flying past the system at high speed. From this new perspective, momentum must still be conserved.
Of course. That's a fundamental principle.
But when you do the math, it doesn't work. If you assume the initial mass of the system is just m plus the two little m's, the books don't balance. Momentum conservation fails.
It fails just because of the stored energy in the springs.
Yes. The only way to make the math work, the only way to conserve momentum, is to assume that the system, when the springs are compressed, is actually heavier.
So the stored potential energy has to have its own mass.
You are mathematically forced to conclude that the potential energy, E sub p, contributes an extra little bit of mass, a delta m, to the system.
And I'm guessing when you solve for that delta M,
You find, inescapably, that delta m equals E sub p divided by c squared. The potential energy stored in the configuration of the system, the V term in our Hamiltonian, has real physical mass.
that's incredible. So a system is heavier when its parts are storing energy. A compressed spring system is heavier.
And a bound system, like an atom, where the binding energy is negative potential energy, is actually lighter than the sum of its parts. The energy configuration directly affects the mass.
What an amazing journey. We started with this philosophical war in the 17th century over MV versus MV squared.
And we end up with this deeply elegant analytical structure, Hamiltonian mechanics, that not only solves classical problems, but provides the language for quantum mechanics and proves mass-energy equivalence.
It's just staggering how the search for elegance and symmetry in the math led to such profound physical truths.
And that's the ongoing story. Most Hamiltonian systems are, in general, chaotic. But the whole goal of advanced physics is to find those hidden symmetries, if you can find enough of them.
Enough of those cyclic coordinates.
Enough conserved quantities, yes. Then the Liouville-Arnold theorem says you can completely solve the system. You can transform it into something simple.
So the key to solving complexity isn't always more computing power.
No. It's about finding the hidden, underlying geometric symmetry of the problem. That's what unlocks it.
Which brings us to a final thought for you to take away. If the power to simplify motion, to understand these incredibly complex problems, comes down to finding unseen symmetries and hidden conserved quantities in the structure of the system. Think about the complex system you're studying right now, whether it's in finance or biology or anything else.
And ask yourself, what unseen symmetry or hidden conserved momentum could unlock the simple, elegant truth of its motion?